Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. They are often used in physical and mathematical problems and are most useful when it is difficult or impossible to use other mathematical methods. Monte Carlo methods are mainly used in three distinct problem classes: optimization, numerical integration, and generating draws from a probability distribution. In physics-related problems, Monte Carlo methods are quite useful for simulating systems with many coupled degrees of freedom, such as fluids, disordered materials, strongly coupled solids, and cellular structures. Other examples include modeling phenomena with significant uncertainty in inputs such as the calculation of risk in business and, in math, evaluation of multidimensional definite integrals with complicated boundary conditions. In application to space and oil exploration problems, Monte Carlo-based predictions of failure, cost overruns and schedule overruns are routinely better than human intuition or alternative, soft methods. In principle, Monte Carlo methods can be used to solve any problem having a probabilistic interpretation. By the law of large numbers, integrals described by the expected value of some random variable can be approximated by taking the empirical mean of independent samples of the variable. When the probability distribution of the variable is parameterized, mathematicians often use a Markov chain Monte Carlo sampler. The central idea is to design a judicious Markov chain model with a prescribed stationary probability distribution. By the ergodic theorem, the stationary distribution is approximated by the empirical measures of the random states of the MCMC sampler. In other important problems, we are interested in generating draws from a sequence of probability distributions satisfying a nonlinear evolution equation. These flows of probability distributions can always be interpreted as the distributions of the random states of a Markov process whose transition probabilities depends on the distributions of the current random states. In other instances, we are given the flow of probability distributions with an increasing level of sampling complexity. These models can also be seen as the evolution of the law of the random states of a nonlinear Markov chain. A natural way to simulate these sophisticated nonlinear Markov processes is to sample a large number of copies of the process, replacing in the evolution equation the unknown distributions of the random states by the sampled empirical measures. In contrast with traditional Monte Carlo and Markov chain Monte Carlo methodologies, these mean field particle techniques rely on sequential, interacting samples. The terminology mean field reflects the fact that each of the samples interacts with the empirical measures of the process. When the size of the system tends to infinity, these random empirical measures converge to the deterministic distribution of the random states of the nonlinear Markov chain, so that the statistical interaction between particles vanishes. Introduction. Monte Carlo methods vary, but tend to follow a particular pattern. Define a domain of possible inputs. Generate inputs randomly from a probability distribution over the domain. Perform a deterministic computation on the inputs. Aggregate the results. For example, consider a circle inscribed in a unit square. Given that the circle and the square have a ratio of areas that is pi 4, the value of pi can be approximated using a Monte Carlo method. Draw a square on the ground, then inscribe a circle within it. Uniformly scatter some objects of uniform size over the square. Count the number of objects inside the circle and the total number of objects. The ratio of the two counts is an estimate of the ratio of the two areas, which is pi 4. Multiply the result by 4 to estimate pi. In this procedure, the domain of inputs is the square that circumscribes our circle. We generate random inputs by scattering grains over the square, then perform a computation on each input. Finally, we aggregate the results to obtain our final result, the approximation of pi. There are two important points to consider here. Firstly, if the grains are not uniformly distributed, then our approximation will be poor. Secondly, there should be a large number of inputs. The approximation is generally poor if only a few grains are randomly dropped into the whole square. On average, the approximation improves as more grains are dropped. Uses of Monte Carlo methods require large amounts of random numbers, and it was their use that spurred the development of pseudorandom number generators, which were far quicker to use than the tables of random numbers that had been previously used for statistical sampling. History. Before the Monte Carlo method was developed, simulations tested a previously understood deterministic problem, and statistical sampling was used to estimate uncertainties in the simulations. Monte Carlo simulations invert this approach, solving deterministic problems using a probabilistic analog. An early variant of the Monte Carlo method can be seen in the Buffon's needle experiment, in which pi can be estimated by dropping needles on a floor made of parallel and equidistant strips. In the 1930s, Enrico Fermi first experimented with the Monte Carlo method while studying neutron diffusion, but did not publish anything on it. The modern version of the Markov chain Monte Carlo method was invented in the late 1940s by Stanislaw Ulam, while he was working on nuclear weapons projects at the Los Alamos National Laboratory. Immediately after Ulam's breakthrough, John von Neumann understood its importance and programmed the ENIAC computer to carry out Monte Carlo calculations. In 1946, physicists at Los Alamos Scientific Laboratory were investigating radiation shielding and the distance that neutrons would likely travel through various materials. Despite having most of the necessary data, such as the average distance a neutron would travel in a substance before it collided with an atomic nucleus, and how much energy the neutron was likely to give off following a collision, the Los Alamos physicists were unable to solve the problem using conventional, deterministic mathematical methods. Stanislaw Ulam had the idea of using random experiments. He recounts his inspiration as follows. The first thoughts and attempts I made to practice the Monte Carlo method were suggested by a question which occurred to me in 1946 as I was convalescing from an illness and playing solitaires. The question was, what are the chances that a Canfield solitaire laid out with 52 cards will come out successfully? After spending a lot of time trying to estimate them by pure combinatorial calculations, I wondered whether a more practical method than abstract thinking might not be to lay it out say 100 times and simply observe and count the number of successful plays. This was already possible to envisage with the beginning of the new era of fast computers, and I immediately thought of problems of neutron diffusion and other questions of mathematical physics, and more generally how to change processes described by certain differential equations into an equivalent form interpretable as a succession of random operations. Later, in 1946, I described the idea to John von Neumann, and we began to plan actual calculations. Stanislaw Ulam being secret, the work of von Neumann and Ulam required a code name. A colleague of von Neumann and Ulam, Nicholas Metropolis, suggested using the name Monte Carlo, which refers to the Monte Carlo casino in Monaco where Ulam's uncle would borrow money from relatives to gamble. Using lists of truly random numbers was extremely slow, but von Neumann developed a way to calculate pseudorandom numbers using the middle square method. Though this method has been criticized as crude, von Neumann was aware of this. He justified it as being faster than any other method at his disposal, and also noted that when it went awry it did so obviously. Unlike methods that could be subtly incorrect, Monte Carlo methods were central to the simulations required for the Manhattan Project. though severely limited by the computational tools at the time. In the 1950s, they were used at Los Alamos for early work relating to the development of the hydrogen bomb, and became popularized in the fields of physics, physical chemistry, and operations research. The RAND Corporation and the U.S. Air Force were two of the major organizations responsible for funding and disseminating information on Monte Carlo methods during this time, and they began to find a wide application in many different fields. The theory of more sophisticated mean field type particle Monte Carlo methods had certainly started by the mid-1960s, with the work of Henry P. McKean, Jr. on Markov interpretations of a class of nonlinear parabolic partial differential equations arising in fluid mechanics. We also quote an earlier pioneering article by Theodore E. Harris and Herman Kahn, published in 1951, using mean field genetic type Monte Carlo methods for estimating particle transmission energies. Mean field genetic type Monte Carlo methodologies are also used as heuristic natural search algorithms in evolutionary computing. The origins of these mean field computational techniques can be traced to 1950 and 1954 with the work of Alan Turing on genetic type, mutation selection learning machines, and the articles by Nils All Baricelli at the Institute for Advanced Study in Princeton, New Jersey. Quantum Monte Carlo, and more specifically diffusion Monte Carlo methods, can also be interpreted as a mean field particle Monte Carlo approximation of Feynman KAC path integrals. The origins of quantum Monte Carlo methods are often attributed to Enrico Fermi and Robert Richmond, who developed in 1948 a mean field particle interpretation of neutron chain reactions. But the first heuristic-like and genetic-type particle algorithm for estimating ground state energies of quantum systems is due to Jack H. Hetherington in 1984 in Molecular Chemistry. The use of genetic heuristic-like particle methodologies can be traced back to 1955 with the seminal work of Marshall N. Rosenbluth and Ariana W. Rosenbluth. The use of sequential Monte Carlo in advanced signal processing and Bayesian inference is more recent. It was in 1993 that Gordon et al. Published in their seminal work the first application of a Monte Carlo resampling algorithm in Bayesian statistical inference. The authors named their algorithm the bootstrap filter, and demonstrated that, compared to other filtering methods, their bootstrap algorithm does not require any assumption about that state space or the noise of the system. We also quote another pioneering article in this field of Genshiro Kitagawa on a related Monte Carlo filter. Particle filters were also developed in signal processing in the early 1989 to 1992 by P. Del Moral, J.C. Neuer, Rigel, and G. Salou in the LAASCNRS in a series of restricted and classified research reports with STCAN, the IT company DIGILOG, and the LAASCNRS on radar, sonar and GPS signal processing problems. These sequential Monte Carlo methodologies can be interpreted as an acceptance-rejection sampler equipped with an interacting recycling mechanism. From 1950 to 1996, all the publications on sequential Monte Carlo methodologies, including the pruning and resample Monte Carlo methods introduced in computational physics and molecular chemistry, present natural and heuristic-like algorithms applied to different situations without a single proof of their consistency, nor a discussion on the bias of the estimates and on genealogical and ancestral tree-based algorithms. The mathematical foundations and the first rigorous analysis of these particle algorithms are due to Pierre Del Moral in 1996. Branching-type particle methodologies with varying population sizes were also developed in the end of the 1990s by Dan Crisan, Jessica Gaines and Terry Lyons, and by Dan Crisan, Pierre Del Moral and Terry Lyons. Further developments in this field were developed in 2000 by P. Del Moral, Guionnet, and L. Michelor. Definitions. There is no consensus on how Monte Carlo should be defined. For example, Ripley defines most probabilistic modeling as stochastic simulation, with Monte Carlo being reserved for Monte Carlo integration and Monte Carlo statistical tests. Sawilowski distinguishes between a simulation, a Monte Carlo method, and a Monte Carlo simulation. A simulation is a fictitious representation of reality. A Monte Carlo method is a technique that can be used to solve a mathematical or statistical problem, and a Monte Carlo simulation uses repeated sampling to determine the properties of some phenomenon. Examples: simulation. Drawing one pseudo-random, uniform variable from the interval 0, 1, can be used to simulate the tossing of a coin. If the value is less than or equal to 0.50, designate the outcome as heads, but if the value is greater than 0.50, designate the outcome as tails. This is a simulation, but not a Monte Carlo simulation. Monte Carlo method. Pouring out a box of coins on a table, and then computing the ratio of coins that land heads versus tails is a Monte Carlo method of determining the behavior of repeated coin tosses, but it is not a simulation. Monte Carlo simulation. Drawing a large number of pseudo-random, uniform variables from the interval 0, 1, and assigning values less than or equal to 0.50 as heads and greater than 0.50 as tails, is a Monte Carlo simulation of the behavior of repeatedly tossing a coin. Carlos and Whitlock point out that such distinctions are not always easy to maintain. For example, the emission of radiation from atoms is a natural stochastic process. It can be simulated directly, or its average behavior can be described by stochastic equations that can themselves be solved using Monte Carlo methods. Indeed, the same computer code can be viewed simultaneously as a natural simulation, or as a solution of the equations by natural sampling. Monte Carlo in random numbers. Monte Carlo simulation methods do not always require truly random numbers to be useful, while for some applications, such as primality testing, unpredictability is vital. Many of the most useful techniques use deterministic, pseudorandom sequences, making it easy to test and rerun simulations. The only quality usually necessary to make good simulations is for the pseudo-random sequence to appear random enough, in a certain sense. What this means depends on the application, but typically they should pass a series of statistical tests, testing that the numbers are uniformly distributed or follow another desired distribution when a large enough number of elements of the sequence are considered is one of the simplest and most common ones. Weak correlations between successive samples is also often desirable, necessary. Sawilowski lists the characteristics of a high-quality Monte Carlo simulation. The number generator has certain characteristics. The number generator produces values that pass tests for randomness. There are enough samples to ensure accurate results. The proper sampling technique is used. The algorithm used is valid for what is being modeled. It simulates the phenomenon in question. Pseudo-random number sampling algorithms are used to transform uniformly distributed pseudo-random numbers into numbers that are distributed according to a given probability distribution. Low discrepancy sequences are often used instead of random sampling from a space, as they ensure even coverage and normally have a faster order of convergence than Monte Carlo simulations using random or pseudo-random sequences. Methods based on their use are called quasi-Monte Carlo methods. Monte Carlo simulation versus what-if scenarios. There are ways of using probabilities that are definitely not Monte Carlo simulations. For example, deterministic modeling using single-point estimates. Each uncertain variable within a model is assigned a best guess estimate. Scenarios for each input variable are chosen, and the results recorded. By contrast, Monte Carlo simulations sample from a probability distribution for each variable to produce hundreds or thousands of possible outcomes. The results are analyzed to get probabilities of different outcomes occurring. For example, a comparison of a spreadsheet construction model run using traditional what-if scenarios, and then running the comparison again with Monte Carlo simulation and triangular probability distributions shows that the Monte Carlo analysis has a narrower range than the what-if analysis. This is because the what-if analysis gives equal weight to all scenarios, while the Monte Carlo method hardly samples in the very low probability regions. The samples in such regions are called rare events.